This is a little bit later. But this video will be on systems and linear momentum, center of mass, impulse and momentum, and the conservation of linear momentum. So we're going to start right here. So momentum is defined as mass times velocity. Actually, I can go back a section here, section 9.1. Something can have momentum because of having lots of mass and little velocity, or lots of velocity and little mass. And we could have momentum. It is a vector. So there's an x component of momentum and a y component of momentum. And in any system, any isolated system, the change of momentum of one object has to equal the change of momentum of the other object in that system. So this here is called the impulse momentum theory. It says that the change of momentum is equal to force divided by time, basically. Force times time. So force is equal to ma, which is m dv dt, which means force times time is equal to mass times change of velocity. M dv is equal to f dt. And you would integrate both sides of that. For an isolated system where energy is not moving in or out, nor is matter moving in or out, the total change of momentum has to be 0. And so this is the change of momentum of the hammer is equal to the negative change of momentum of the nail. So if the hammer lost 5 kg per second of momentum, then the nail would gain 5 kg per second of momentum. And that's related to Newton's third law, which says that for every force, there's an equal and opposite force. And it's written here. Whenever two or more particles in an isolated system interact, the total momentum of the system does not change. It may be transferred from one object to the next, but it will not change overall. For something that is not isolated, if there is an external force acting on an object, then the change of momentum, which is the impulse, is the integral of f dt. Again, this is part of the impulse momentum theory. So if you have a force versus time graph, the impulse is the area under the curve. Or you could say the average force times time. Here's the impulse momentum theory again. Integral of f dt is equal to the integral of m dv. Change of momentum is equal to the impulse of the net force acting on the particle. Again, a non-isolated system, you can have energy that comes in or leaves. All right, so collisions. The rule is for collisions in an isolated system, the change of momentum of one object will equal the change of momentum of the second object. We have two different types of collisions. An elastic collision is one in which the total kinetic energy of the system as well as the total momentum of the system remains constant. And for that, you kind of get into some fun algebra. And then an inelastic collision, kinetic energy is not conserved, but momentum is. Momentum is always conserved in an isolated system. If it's perfectly inelastic, when objects collide and stick together, that's called perfectly inelastic or completely inelastic. Generally, inelastic collisions are hard to analyze without additional information. Lack of this information appears in the mathematical representation as having more unknowns than equations. So it's hard to solve those. Perfectly inelastic collisions, again, they stick together. Those tend to be a little easier to solve. For elastic collisions, you have two equations. The total momentum remains constant, and the total kinetic energy remains constant. And when you get the variables and you substitute them in, you get lovely formulas. So here, what is this? We're talking about Newton's cradle. This is conservation of momentum and conservation of kinetic energy. It consists of 5 identical hard balls supported by strings of equal length, where this kinetic energy is transferred to this one, this one, this one, this one, and basically this one comes off the end back here. It just goes back and forth and back and forth. Ballistic pendulum is a common problem on these. You shoot a bullet toward a block of wood. It inelastically combines with the block of wood. So you can figure out that the total mass would be the sum of the bullet plus the block of wood. And then it rises to some height. And so the rising from here to here is conservation of mechanical energy, where the kinetic energy right here is all transferred to gravitational potential energy at this point. And springs. We have collision. Well, if you have a spring that then lets go, it'll give momentum to both objects. But the momentum of this object and that object has to be the same in magnitude if they're like flying apart. But this one actually shows you've got 2 blocks that are coming together, and they're going to compress the spring, and then it's going to send one off again. So this is just basically a collision, inelastic collision. If you have 2 dimensions, split everything into x and y components and work in x components and y components. Recombine at the end. All right, center of mass is where you would model the whole object applying its mass. If it's a mass, system of a lot of different stuff. Center of mass, the algebraic formula, m1 x1 plus m2 x2 all over m1 plus x plus m2. The integral form of center of mass, which is not on your formula sheet, is that x center of mass is integral of x dm divided by the integral of dm. Let's see if it's on here. Yeah, so they've got integral of r dm divided by the total mass, which I would say integral of x dm divided by the integral of m, like just dm. We did a fair number of those at the time. If you have a number of different particles, the velocity of that whole system would be the velocity of the center of mass of the system. And the acceleration of the whole system would be the acceleration of the center of mass of the system. And notice these equations are very similar to the center of mass formula, except now it's like integral of v dm over total mass. And this is integral of a dm over total mass. Here we go. The center of mass of a system of particles having combined mass m moves like an equivalent single particle of mass m would move under the influence of a net external force. So the total momentum is equal to the impulse. So if a projectile exploded at this point, the total center of mass would still continue along the same path that it was continuing before. Even if it exploded and one piece went here, one piece went there, one piece went that way, and one piece went that way, the total momentum of the system, since there were no external forces acting on it, would still continue along this path. If you have a deformable system, you can still say the change in momentum is equal to integral of f dt. This was the wall's force on the objects. You have to take into account conservation momentum for the system, but then external force from the wall or from the spring or from whatever. Rockets work because propels this piece here, which propels this piece forward. It's just an explosion. It's conservation momentum. Conservation momentum. And I think that's all for that. Again, I gave y'all kind of an integral formula here. Integral of x dm over integral of dm. Let's see, is that everything? Center of mass, impulse momentum, conservation of linear momentum. That's it for that one. Okay. 2 more.